Okay, I'll continue discussions today on electro-optic modulators, and whereas in the last talk I talked about conventional electro-optic materials, nonlinear optic materials like lithium niobate, lithium tantalate, today I'll talk about new types of materials grown by MB or MOVP, which are called quantum confined layers, where we get interesting excitonic effects, as I've discussed before. So I'll be talking about quantum confined Stark effect, called QCSE for short. The basic ideas have been already discussed when I talked about excitons in quantum structures. Then I'll go on to discuss self-electro-optic devices, which can be used as switches. SEED for short. And finally, I'll talk a little bit about injection. These are all types of modulators, about injection modulation of lasers. That is just by switching the current on and off. I'll see that there are some drawbacks in that mechanism also. Let's start with quantum confined Stark effect. We've already seen that things like indium phosphide and gallium arsenide, they belong to zinc blende structure, and they are non-centrosymmetric. Now, this asymmetry is obviously accentuated by the growth of layers when we have a substrate on which we grow epitaxial layers. Then if there is any strain, for example, if this is the substrate here, okay, suppose there is compressive strain here, then obviously there will be tensile strain there, and suppose there are many layers in a multi-quantum well structure, then obviously the symmetry here will depart from cubic. This will be tetragonal symmetry. Okay, there will these unit cell will have same lattice parameter here, same lattice. Okay, but perhaps something like that. A1, A2 not equal to A3. Okay. So this method of growth, strain layer growth, is going to accentuate the asymmetry of these layers and give rise to nonlinear effects. In optics, this phenomena is called birefringence. You have two refractive indices at least in different directions, and this is given by the index ellipsoid, which I discussed last time. Typically x squared over n rx squared plus y squared. N r is the refractive index in the x, y, and the z directions. Is equal to 1. and Z is the direction of propagation. In general, electro-optic effects can be classified into two categories: delta NR squared, change with respect to the electric field. There is a linear component, RLE, which is known in the literature much earlier as the Pockels effect. For example, this is seen in liquids, in electro-optic liquids. It is used in Q-switching lasers, and we have a term SQE squared, which is quadratic, and this is the Kerr effect. Okay, let's take the Pockels effect. Delta NR squared I is equal to Rij, J going from 1 to 3, Ej, electric field. As we've seen, this Rijl is a 6 by 3 matrix. So it's very similar to what we've already seen for lithium niobate, etc. And for gallium arsenide, we know that R41 is equal to R52 is equal to R63. Okay, and this is a bit of a repetition. Rijl in 10 to the power minus 12 meters per volt. Okay, for gallium arsenide, this is 1.6 for KDP. Values are much larger, 10.6 for R63L, and for lithium niobate, this is 30.8 R33L. Okay, this is conventional bulk Pockels coefficients. Okay, now what happens when we grow quantum wells? Because of the layered type of structure, we obviously have additional anisotropy. The properties of the layers are not the same parallel to the layers and perpendicular to the layers. Okay, so we have, if we have waves propagating in both directions, then we have a change in phase. But beta is the propagation constant, beta TE minus beta Tm into L. This is equal to delta NR. L is the length of the sample, and 2 pi by into 2 pi by lambda, where delta NR is the difference in refractive index between parallel polarization and perpendicular polarization with respect to the layer planes. Now, considering optical propagation, it is reasonably simple to, I'll just give you the results, to derive the values of NR parallel. This is just D1 NR1 squared plus D2 NR2 squared over D1 plus D2, where we're talking about now optical properties of the quantum wells, right? So we're talking about D1 is the width of the well, and let's say D2 is the width of the barrier. NR1 is the refractive index of the well, and NR2 is the refractive index of the barrier. And you can see it's quite obviously fairly straightforward and symmetrical. The overall width of this unit cell is D1 plus D2, and NR perpendicular squared will be NR1 squared NR into NR2 squared D1 plus D2. You could even try and derive this from first principles, from propagation of light in this. It's a two layer medium. Okay. Okay. So these are not equal, and hence you get delta NR is NR perpendicular minus NR that is not equal to 0. That's a finite value. Okay, and if you just think of the physics of this, not only are the D1s and D2s are different, but the important thing is the NR1 and NR2s are different, right? Okay. Why? Because typically this is say gas, and for quantum well you can make this where the optics are concerned. You can make this aluminum arsenide. You don't have to go for gallium aluminum arsenide. You can get, in order to get the maximum change in refractive index, you can make this aluminum arsenide. Okay, and for a multi-quantum well, what is D1? D1 would be the NZ into D1, and that's the number of wells, okay, and D2 is the number of barriers, NB, into D2, okay. So you can accentuate the differences by having a large number of wells and barriers. Remember, gallium arsenide, what is the refractive index? Is typically something like 3.3. Yeah. 3.67. Okay. And aluminum arsenide? Come on, it must. Yeah, aluminum arsenide is less. It's about 2.7 to 2.9. About 2.9 as far as 2 point something. It's about 2.9. Okay, so there's quite a lot of difference. Okay, aluminum arsenide is it has to be less. Okay. So if you plug these in, then you find that delta phi is equal to delta NL 2 pi by lambda plus pi L by lambda NR0 cubed minus plus R41L. Okay, gallium arsenide. R41 is something that is non-zero, okay, into EZ plus S12Q minus S11Q into EZ squared. This is a general term, okay, this is a general expression, but this is the quadratic and this is the linear term. Okay, so the idea is that if you design the system properly, you can get fairly large phase shifts of the orders of, this is delta phi in degrees, this is in, okay, this is 40. For indium 0.53 plus X, gallium 0.47 minus X. Okay, arsenic over indium phosphide. Okay. Suppose X is equal to 0, then you have lattice matching. Okay, so then you get X is equal to plus 0.47. It's compressive. X is equal to plus 0.07. Okay, so that is, you get a larger phase shift, and here if X is minus 0.07. Okay, this is obviously tensile, this is compressive. You get a smaller phase shift. This is indium phosphide from multi-quantum wells. I think this must be the number of wells equal to number of barriers, I think. So you see, this is acting just like a conventional lithium niobate type of device. You have suppose you have a structure like that, okay, and you have light coming in, and you have the polarizer analyzer system. Obviously, you have to apply electric field, okay, and because these layer dimensions are very small, okay, even 1 volt across 1 micron is 10 to the power 4 volts per centimeter. Okay, so if you here the light is polarized like that. Normally, okay, if electric field is 0, okay, then there is no output. But if you apply an electric field, then there's a change in the angle of polarization, okay, and then you will get a signal coming out. Because this is normally, if it's inactive, the plane of polarization is vertical, it will go through and it will be cut off by this analyzer. Okay, but if this electroactive, then there will be a change of polarization and some light will get through. So it's a simple illustration of how this MQW device works. Okay, now, so obviously you're getting nonlinear effects due to induced anisotropy. Okay, and this can be illustrated by what I've shown earlier. That if you can see this, okay, this is a typical quantum well structure. This is a gas-al-gas type of structure, okay, and you see that depending upon, this is just illustrating the properties of these wells. If you have, this is wavelength, okay, and this is photoluminescence, okay, and you find that depending upon, okay, this is just not just the quantum well effect, 50 angstrom, 75, 100, 150, okay, this is the quantum confined shift. If you have a very narrow well, then the wavelength of PL is short. If you have a wide well, then this is getting towards the bulk. This is 300K. Okay, this is useful for lasers and things like that. But look at the absorbance. This is absorbance versus wavelength. Okay, and you find that these excitonic effects are coming in. Okay, with different width. And in order to illustrate what is the quantum confined Stark effect, if you see this, photon energy versus absorption coefficient, right? Suppose these are excitonic effects which are seen at room temperature in quantum confined structures. In bulk materials, these effects are observable only at low temperature. Okay, so at 10 to the power 4 volts per centimeter, you have the excitonic peak at this energy. Okay, this is energy. And as you increase the electric field, 10 to the power 4.7, this peak shifts towards lower wavelengths. Okay, lower wavelengths. So obviously, you can see that the effects are twofold. One is that there is a shift of this peak to lower wavelengths, and there is a smearing. Okay, there's a band tailing effect. Okay, this is much sharper, and since this is obtainable with the voltages of the order of 10 to the power 4 volts per centimeter, that means over a micron, that's just a 1 volt. A few volts over a micron. So these are practically realizable. Whereas in the lithium niobate devices, remember, we're talking about 10,000 volts, etc. Okay, that becomes rather clumsy to have a driver, having voltages requiring voltages of thousands of volts. And so the phenomena is you can quite easily understand how modulator can work. Suppose you have a laser which is emitting at this wavelength. Okay, there's no electric field, then the absorbance is very small, the light is getting through. As you're applying field here, okay, in this case the absorbance suddenly shoots up. Okay, and so the laser is so this is the absorption coefficient. Okay. So the light is absorbed, and very little light gets through. So this is based on electroabsorption. Okay, the absorption coefficient is being changed rather than the refractive index. Okay, and so this illustrates a modulator. In which, okay, alpha the same thing. Okay, suppose you have the lasers there, then with electric field the absorption goes something like this. Okay, so what you have a system in which you have and suppose you have a detector here. What is the detected signal? When E is high, okay, then detected signal is 0. And when E is low, then the detected signal, and this is the applied voltage E. So this switch is being turned on or off very fast, and because it's an electric field effect, it is not charge injection. Okay, it is not minority carrier recombination effects, etc., are not coming in. So this can work at very high speeds. Okay, and now one can take this step further by talking about what is known as the self-electro-optic effect. This is a seed device which acts as a switch. This just shows the structure. I'll explain the working just after this. What is this doing? We want a binary switch. The light itself should alter the transparency of this. Okay. So, for example, you can quite easily understand that suppose you have weak light coming in, okay, and light is accompanied by an electric field. Electric field is low. It is not having much effect on this MQW structure, and the light is going through. Okay. Now, if the light intensity goes above a certain value, what can happen? The electric field due to the light can be large, so it will induce the electro-optic effect. The light itself, that's why it's called self-electro-optic effect, and as a result, the switch will turn off. Okay. Okay. So it will be like a binary switch. Okay. And the reason why people were very excited about things like this is that in other words, you are having like a flip-flop circuit which is used in electronics. You have a circuit in which for a seed device, okay, suppose P power in of the input light and power out, what will be the characteristic at the beginning? Okay, with that low intensities, the power will increase. Okay, output power and input power will linearly increase. Okay, then when it comes to that high field where self-absorption sets in, there will be a sudden decrease. Okay, and then after the decrease, it'll increase. Okay. Now, suppose from here you are decreasing the input intensity. Okay, the in that MQW there can be some space charge effects, and so it will not switch back at exactly the same point, but it will switch back here. Okay, so you have a hysteresis. Okay. Between the input power and the output power. So this is simulating what is known as a a bistable device, okay, a flip flop, which will have a characteristic, something like this. So depending upon it can have zero state or one state. Okay, so these this is what is known as optical in this region. Okay, you have what is known as optical bistability. And one can get very fast switches. In fact, once this was demonstrated, it was thought that one could get totally optical computers. Okay. Notice in this case, there is no electric field required, no separated electric field. Light is switching the thing on and off. Okay. So it's an all optical device. This is a all optical device, whereas the other electro-optical, QCSC, you're applying an electric field and you're changing things. So this is an all optical device.
But to operate device, electric.
Pardon?
To operate device.
No, I mean,
some biasing to device.
No, sorry, if the intensity of light will be high, then no bias is required.
Yeah, then no bias is required. Yeah. And you can have this sort of structure also, as I've shown. In some cases, yeah, if you want to change, if you want an electrical signal, then you can take the signal across this R. Okay. So, idea is that this is a device rather like a simple device that we use in sunglass photochromic effect. Okay. This is a much more sophisticated version of what is known as the photochromic effect. What is that? That self-darkening. We have windows which, with high intensity, they darken, okay, and then at low intensities they bleach out. Okay, but this is rather slow. Photochromic effect takes seconds of time, whereas this self-electro-optic device, it's been shown that it can work at frequencies of let's see. Yeah, okay. I have a graph here that if you can, again, like electrical devices, you have a plot of power versus time. Okay. Not frequency, but okay. If you want, this is say per bits in watts. And time going from 10 to the power minus 15 seconds to 1 second. Okay. Now, if I just draw a sort of a general line, this is for say 1 picojoule. Semiconductor devices operate somewhere here. Okay, Josephson devices operate somewhere in this region, and optical device limits are somewhere around this region. So, it's not quite as fast as Josephson devices, but the advantage is that the power ratings are, this is of the order of 10 to the power minus 12 to going to 10 to the power minus 3 watts. Okay. So, these optical devices do have a particular range where they may be useful, and there was a trend to try and have all optical computers, but that is currently not very attractive because the interfacing with electronics is still a problem. So it's more optoelectronic rather than all optical. Okay, let me just go back a little bit and talk about electrical switching of lasers, because to a large extent still especially semiconductor lasers which have the easiest way of modulating a semiconductor laser is to change the current through it. Okay, and so you can the currents are of the order of milliamps. You can just by changing the injection current. This is still obviously the most easy. However, it is when the speed becomes very fast, then there are problems, and that's why I just wanted to mention this here. Suppose you have very fast current pulses of this type, of the going down to nanoseconds, but if you look at the light output does not follow this. There may be some slight turn on delay, and then the light will so the light will suffer a certain turn on delay, which is small, but if you go down to, remember we're getting into the range of gigahertz, so this tau d is dependent upon the minority carrier lifetime, because after all, the semiconductor lasers, we are injecting minority carriers from the p-type and the n-type side, and this is quite easily analyzed in most of the textbooks. For example, in a p-type semiconductor, if you write the continuity equation for electrons, then the rate of change of the electron concentration is just given by the generation rate minus the recombination rate. Okay, so the generation rate is the injected current, okay, into volume, and this is just the number, okay, minus n by tau e. So this is the generation rate, and this is the recombination rate. Okay, so if we solve this equation, we find that nt is tau e I over q a d, 1 minus exponential, and obviously you'll expect an exponential variation, minus d by tau e, for you take n0 at t equal to 0 is equal to 0, or t is tau e log I over 1 minus q nt a d by tau 0. Okay, a laser is a device which requires a certain threshold current. Okay, so when this nt, when does lasering action start? When nt reaches n threshold. Okay. So we know for the threshold condition, ITH is q nth a d by tau e. So since we are defining this delay time is the time at which nt is equal to n threshold. Okay. Remember the IV characteristic of a laser, okay, is something like this. Okay, so say this is the light output versus I current. Okay, so certain amount of time goes into getting enough carriers to reach threshold. So if we just substitute in that previous equation, then we find that what is the delay time? That is equal to tau e log I over I minus ith. It's a fairly simple expression. So you see that it depends upon this minority carrier recombination time, and it's log I over ith. Okay. So we want to decrease TD. How can we do that? Suppose if laser is pre-biased, that means, instead of switching on right from here, suppose we pre-bias it to a certain level, to a current to something I0 just less than ITH, and the initial condition for n corresponding to n I0 is n0 is equal to I0 tau E by AQD. Then instead of this going from 0 to ITH, okay, then what happens is that tau D is tau E, and it's exactly the same expression, but I minus I0 over I minus ITH. Okay. Okay. And if this is, obviously this is going to be less than the previous case, and if we illustrate this by what is the tau D in nanoseconds, I over I minus ITH. So if we have, it's a p-type semiconductor, we are saying that, okay, suppose Na is equal to 2 × 10⁻17, then the variation is like that. 2.7 × 10⁻19. As Na is increasing, okay, the delay time is decreasing. Why is that? Because of obviously the larger, more p-type material, the minority carrier lifetime tau E is decreasing. Tau E is essentially the minority carrier lifetime in p-type materials, that is 4 electrons. Okay, and so, and obviously if you are if you can increase this, okay, then this is without pre-biasing. Okay, if the threshold current increases, then obviously the delay increases. Okay, threshold current increases, the delay increases.
So without pre-biasing, if we lower down ITH?
Yeah, obviously, sure. That is the other reason. If you can, if you have it, then obviously you have to have a different design of a laser. Okay, if you can reduce ITH, yeah, you can either use pre-biasing or. This is also especially in the case when ITH was of the order of amps, okay, or you can reduce ITH, okay. But if it's milliamps, okay, fine, reduce ITH, okay. And for example, okay, what is the modulation frequency that you get? In gigahertz, going from say 0 to say 2.5. Okay. As a function, okay, this is in dB. Okay, this is the output in dB minus say 25 or whatever. Okay. Now, if you have I by ITH is rather small, okay, just a little more than the just a little more than threshold, then the frequency response falls. Okay, but if you keep on increasing this, that means you're injecting more. I by ITH is maximum current that you're injecting is 1.3 times the threshold. Okay, then the frequency response is much faster. And this is a nominal modulated output in dB. Okay, so this concludes discussion of injection modulation. Injection modulation is pretty successful in most electro optical communication systems. This is the method that is still employed, but in case of if you want to go to very high frequencies, then you may go to apart from injection modulation, you can go to nonlinear optic materials, or going to for QCSE type of devices.